Hi, everyone. Hi, professors. Hi, students. Yes, I am Montserrat Rivas, and I have the honor to be now and for 2 years the president of the Spanish Club of Magnetism. And this is an association gathering more than 150 researchers working in magnetism, either in Spain or even some of them they're abroad, and they're collaborating with friends of Spanish researchers. And we also, additionally to that, have a lot of students working now in their PhDs, their postdocs, or even undergraduate in magnetism, very interested by magnetism. So we're very happy to be helping here a little bit in this workshop on Spintronics, because actually Spintronics, of course, is a very, very crucial part of the research done in the Spanish Club of Magnetism. And then we have today a session of 2.5 hours or 3 hours ahead of us. And we are so lucky to count on 3 excellent speakers, exponents of nowadays research on spintronics. I am very honored to introduce in the first place Professor Dr. Jairo Sinova. And Professor Sinova is an Alexander von Humboldt Professor of Physics at Johannes Gutenberg Universität, Mainz. After completing his doctorate that was in Indiana University, he became a postdoc at the University of Tennessee and the University of Texas at Austin, before then becoming a professor of physics at Texas A&M University. And among his honors, Professor Sinova has received the Alexander von Humboldt Professorship Award, the Johannes Gutenberg Research Fellowship, the ERC Advanced Synergy Grant, National Science Foundation's Career Award, the Cottrell Scholar Award, and was selected a Fellow of the American Physical Society. That's a lot. But I think what he will like more to say is that he leads the INSPIRE group, very inspiring name for your group. And they are devoted to spintronics and nanoelectronics, with a special focus on spintronics and mesoscopic electronic transport. Some of their main contributions are related to spin Hall effects and diluted magnetic semiconductor physics. I have to add that Professor Sinova is very fond of wines, and this is maybe why we are seeing him in a wine cellar. Are you in a wine cellar, Jairo?
That's the picture of my wine cellar. I'm not in the wine cellar right now, but this is how I survived COVID.
I see. Excellent. Very good. A couple of years ago, we were in Mainz for GEMS that you were hosting, and actually all the Spanish community, we felt very welcome at this conference there by you. So we would like very much to welcome you now in Zaragoza or in Llanes, but unfortunately cannot be. We're very happy to see you through this screen. So whenever you want to start talking, Jairo, when you're ready.
Great, thank you. Thank you, Montse. Thank you, Fernando, and thank you everybody to put this together. I'll go ahead and start sharing the screen here. And I'll put my first slide up. Just wanted to say that it's an honor to be here and always a privilege to connect again to Spain. You know, many people don't realize that I'm actually Spanish. I'm from Valladolid. I left Spain when I was 16 years old for an exchange student for 1 year, and it became 25 years exchange. And then in the way back, I made it almost back, but you know, a little deviated to Germany. So it'll be a pleasure to see you all when all this crisis is over. So my first, then of course I don't, Fernando said there was a lot of young people. I don't count on among those, unfortunately. Felix does, but I don't. Yeah. So then today, the first lecture, it was not so much intended as a tutorial, but more of a motivation of why should you study this? You know, what comes along with this? What are the discoveries that we're doing, and what is there left for you to do as a student? And here, this is the motivation of my talk at this moment. So it would be maybe a little bit of a rapid example of some of the things that we can do and expect, and the things that you will be learning So, the title was given to me by Fernando of Why Spintronics, but I give a subtitle of From Magnetic Cast to Artificial Intelligence, the Circular Technological Revolution of Spintronics. So hopefully you enjoy it. So as you guys have started, you're all students and you're starting your scientific career, you can look up in scale and think of the cosmos and things like that, or choose to go in a different direction, which is the smaller scale, which is just as fascinating in the micrometers, millimeter, micrometers, and all the way to the atomic scale in the Schrödinger world, which is the world that you've chosen to engage in, where the electron is king, essentially, where you actually are not really looking at atomistic, at high energy physics, and you will do actually. And this electron, of course, has two characteristics to them, two personalities, split personalities in a sense. One is the charge, which you can manipulate easily by electric currents, and the other one is the spin, which is the quantum compass that we can manipulate like a magnet. Now, naturally, these two characters of the spin come into technology as I said, in split personalities that don't know much of each other. Most of the time, charge is the one being utilized to compute, and it is still majority of storage of information is based on magnetic storage information, even though all your SD cards and laptops are based, of course, on solid state memories. But those can assure you they don't last so long. The ones that the cloud, the responsibility of the cloud is actually based on magnetism. And as you know, the first really spintronic revolution came in the information storage itself, where you can see I like to call it this evolution from analog to digital, from ink to spin. Now I'm in Johannes Gutenberg University in Mainz. So I'm contractually engaged to tell you that the first and best example of the analog was the Gutenberg Bible, which created actually the first information revolution in the world. Before that, there were only, books were counted in the number of thousands. And after the movement trace that he created, it was in the millions after a few years. But as you can see here, the actual digitalization of information has made a huge leap from about 2010, in less than a decade, in about a decade and a half. Now we are essentially 1999, all the nines you want to put is all primarily digital. This revolution, of course, occurred by the discovery of the GMR effect, the giant magnetic resistance effect, which you will learn about in this school. It was first discovered by Albert Wirth and Peter Grunberg independently. And primarily what made it a revolution is the work of Stuart Parkin that brought it from the lab to the hand, essentially, by showing this beautiful growth of these multi-layer systems that allows for the manipulation and of these domains and very high density readheads. But of course, he got the Millennium Prize for that, so he didn't get to share the Nobel Prize, unfortunately. Now, that you will learn about this, of course, throughout the course, but why spin? Why are we thinking of spintronics, and why such a broad part within actually magnetism? Because the spin is really the multi-connector. We also have a center that actually called the SPICE, the Spin Phenomena Center, that actually tries to bring a lot of the schools and workshops of different areas, because here, not only at the solid state level, you have these things, but you have in the high energy physics and nuclear physics, many spintronics concepts come directly from it and borrowed. And now, of course, we're doing high energy physics effectively in the solid state environment due to spintronics, spin effects, spin-orbit coupling. Chemists comes ubiquitous to actually create new materials. As you will see, we have a plethora of new materials and exciting new materials with novel properties that you wouldn't expect otherwise. A lot of it connected by a spin, the spin phenomena. Mathematically, with the topology and all these things come directly from the spin phenomenon, the coupling and the intertwine that happens within the band structures and momentum space and in real space. And of course, engineering and the practical aspects of it. I like, so I'm not going to maybe get in trouble by the quote that I like to say, engineering, you have this practical aspect of applications, but I believe more like in the Feynman quote, that physics, to a physicist at least, is like sex. It has practical consequences, but that's not why we do it. It's really this fascination of the physics that is actually comes along with it. that is what fascinates us to do it. So in this course, I'm just the beginning. I'm not really giving you a lecture itself, but you're going to learn lots of these things. You're going to learn from a spin transport. You have a fantastic lineup of, when I was a student, I would have loved to have had such a lineup in front of me, except for me. But then you're going to learn about spin transport phenomena, magnetization dynamics, of how to manipulate the magnetization both at the level of antiferromagnets and ferromagnets, how to the spin textures come along in all kinds of shapes and sizes, from skyrmions to MFM techniques, to topological charges and topological effects in high energy physics that you see in these topological textures. A thing called spin orbitronics, which essentially is also coupled to this idea of spin textures now in momentum space, creating the spin Hall effects and batteries that you can see. The engineering of emerging new materials that have, as I say, both in the two-dimensional oxide, antiferromagnetic spintronics that I'm going to tell you a little bit about, since this is the thing that I'm doing a little bit more about, and molecular spintronics, which has a lot of exciting aspects that Luis will tell you later. And within the calculation and measuring and applications is another exciting thing, which I'm also going to connect to, where you can have both new ways of using artificial intelligence to do computation, as well as creating solid state spintronics-based artificial intelligence platforms, which is very exciting, and Julie will tell you lots about later on in the course. So please, I know these 2 weeks are tough to actually make them to all the classes, but please make the effort, because each of these researchers that I see in the list are magnificent and really have created a lot of these physics that they will actually explain to you. So I really recommend that you do attend those. So let me now give you a little bit of the story of this idea that I mentioned about creating magnetic hats and this artificial intelligence, and just give you an overview of some rapid developments that have happened in the last few years, touching now on some aspects of the things that are covering, to give you an idea of how rapid the developments are in the field, and also that these developments you have to shape. You as students are the ones that are actually leading them. So, the read heads you know about now, most of you, essentially you have a nice read head that is essentially now the sensitivity to actually detect and manipulate. That's where the tunnel magnetic resistance and GMR effects and PMR that comes into play, that you will learn from the next lectures, come into play and allow you to create these very high density disk drives. But these are the ones that are responsible for all of the now cloud computing that you've been able to enjoy. So this itself is really where the cloud computing has come from, not from the ones on your laptops, but for the cheap, high throughput density storage that now is in these farms, in the sense of data farms that we enjoy. On the other hand, what is the next thing that we do in memory? Because here, our goal, your goal, is not to think what you have now, what you're enjoying now technologically, but you will be needing in 30 years or so, and the challenges, the grand challenge that you face. In here is not to segregate, because here the idea is, unfortunately, is that both the computationally and the data storage and the doing of storage is segregated at the moment. We want to integrate it to make it faster and more reliable. And the idea is to essentially go towards MRAM technology, magnetic random access memories, which started using this old century switching by currents of different flips. But nowadays we're trying to do what is called a spin transfer MRAM technology. This is actually done, as you will probably hear later on by Andy, I think is going to cover this, spin transfer torque. I don't put the equation is grayed out, you can see it later, but essentially the idea is that you have a ferromagnet, something in between, which is a normal metal without a ferromagnet, another ferromagnet. This one tends to be pinned. And as you drive current through one to the other, you will be able to flip the one that is free to move, depending on the sign of the current. Essentially, you transfer angular momentum from one to the other. This type of physics, of Lonsesky and Berger predicted it, is the one that has now been used to actually create solid state memories, MRAM, magnetic random access memory, with no moving parts, okay? The actual hard disk drives, unfortunately, they do crash. because of their mechanical, beautiful mechanical aspects to them. But if you actually do the analogy, you're essentially going at the speed of Mach 3, 3 times the speed of sound, if you actually convert the actual distance that is actually above the disk to 1 meter. And this is like going across the world at Mach 3 without hitting anything and tell you which lights are on and off all the time. Now, in this case, to make it more reliable, you try to make it that there's no moving parts. On the other hand, here, it is more scalable. You actually making this technology where you actually, through the magnetic tunnel junctions, you drive your current. But at some point, the heating can get to you because the breakdown voltage and the writing voltage can actually overlap at some point and melt down. So in a sense, instead of a crash, you have a meltdown of memory. And this is where one alternative was thought out, and then this is what has been working on the last 10 years, maybe, to alternatives to electric currents, polarized electric currents feeding you this strong drive to actually do it that you do essentially spin currents. And this is something that you know from the spin, from the wave that you do in the actual stadiums, that you can transfer information. You can transfer angular momentum without transferring energy, without creating heat. And this is the notion of using spin currents that can actually be created by the spin orbit coupling. And the spin orbit coupling comes into spintronics very forcefully by connecting the spin and charge degrees of freedom through the Pauli, through the Dirac equation. This is essentially this connection. This connects the electron and the spin dependent through a spin dependent force that is utilized nowadays as creating forms of generating spin currents. One of the effects, of course, is the spin Hall effect, as it was mentioned. This is something that I've done for quite a long time, and this is the idea that you run a current through a normal metal, so essentially it's unpolarized metal, but has spin orbit coupling, and in this particular case, it's better. And it doesn't have to be, but it's better that it's inversion symmetry broken, although in this case it's not required by symmetry, and there will be a spin current perpendicular to this charge current that you drive. And this spin current, this angular momentum current, can be utilized or injected in different places. There's another corollary effect, which is called the inverse spin galvanic Edelstein effect. And the idea here is that as you run the current, you actually polarize the entire current perpendicular also to this thing, but you're not creating a spin current itself. Here you can see there's a current, and you will see that from Sergio Valenzuela will actually tell you about it in more detail, because the spin downs are reflected one way, the spin ups are reflected the other way, but you have an effective perpendicular spin current to the charge current. Here you have an effective, you're magnetizing your system without creating a current perpendicular to it, but proportional to the electric field that you apply. This is important because from there you can actually do many things. So the spin Hall effect is connected to the anomalous Hall effect in magnetism, which has been a major characteristic of detecting topological effects, etc., and detecting magnets at different stages, and has also been a generator of essentially the precursor of the topological insulators by the discovery of the quantum spin Hall effect as well. But here, I wanted to show you how, for example, we've been able to learn from the spin Hall effect to create a spin Hall effect MRAM technology in a very short time. The idea here is that we want to go from this problem that the technology has, that essentially you can heat up the system too much and essentially melt down, to where you run your current not through the most resistive part of your system, but above in the metallic part, so it's not so heating, so you don't have any problem of breakdown, but being able to flip the one above and control this one, okay, by the spin Hall effect, effectively, or the Edelstein effect. This is where there were some experiments now a decade ago, exactly a decade ago, by Carantella and their group, Miron as well, led by Miron, the student, and then where they ran the current through in the lower part of this platinum, and there was then two effects. One, a spin current, an Edelstein effect coupled to the lower layer here that could flip because it would detect a polarization proportional to the current. And there would also be an injection of spin current due to the spin Hall effect, that would actually also flip the ferromagnet. Both of them in here, the idea is that you can detect which ones they are depending on the symmetry of the torque, which you have means to detect by effective FMR, ferromagnetic resonance experiments, where in this case, this small magnetic field that you're creating is internally within momentum space that you have in here. Now, I don't want to go into any details of what it is. It's just that two are mixed. But the key idea that in this problem, you didn't know which one was coming in. It was the spin Hall effect and the Edelstein effect. How would you go? And you still had to have this notion that you have to have a second element that brings this spin current to flip your ferromagnet to create these devices. Now, what about creating one that it flips itself? Because internally you can create those effective magnetic fields due to spin orbit coupling. And with that internal field that you create through the currents, it's like a cat flipping itself. This can be done, and I will go, again, if you have any questions, I'll have all the slides that I can show you later on how it all works. You will hear it in some aspects on the lectures later. But the idea is to actually go to a ferromagnet, in this case, gallium manganese arsenide, that is itself has broken inversion symmetry. So the bulk ferromagnet itself has that symmetry broken. You don't have to break it by the device that you create, by creating a structural inversion symmetry. And then you can detect in here, depending on the direction of the current, you can excite the magnetization and effect flip it or change the direction of the magnetization. And in this sense, you're creating a magnetic cat, meaning that the cat, as you know, if it's able to transfer angular momentum from one part of its body to the other part in order to actually always land on its pose. This is essentially internal transfer of angular momentum. That's what the cat is doing. It has a total of 0, but it's creating that internal one. And this is essentially what you've achieved by doing this type of notion of creating these MRAMs without melting. But in this case, with a single ferromagnet. Now, this is nice. We've achieved that. It's a nice thing to do. But what next? You have to think of the challenges. One problem is faster. It's solved, and essentially you've integrated that now by integrating this spin orbit coupling physics in a single ferromagnet, that you're able to show with this physics that you can flip the ferromagnet, in principle at least. But just as in the Olympics, you have the motto of faster, higher, and stronger. Now, in the Techno Olympics, Tech Olympics, you actually have a slightly different mottos, which is faster, higher efficiency, stronger connectivity. And those are part of the grand challenges that Spintronics in many ways tries to address. We've now done faster. So these devices themselves, this MRAC technology, particularly the spin orbit torque-based MRAC technology, tends to be faster for several reasons, technological reasons. But what about higher efficiency and stronger? And what are the grand challenges? Why do we need to worry about this? Well, the higher efficiency is a little obvious, but I don't know if you know, and I don't want to make you feel bad about it, but it's just the fact that for every 30 Google searches that you do, okay, you boil 1 liter of water. That's the energy that it takes for every search. Whenever you're looking up a word, whenever you want to do the translation, it doesn't matter. Essentially, you're boiling. So you boil a lot of water during the day, most likely. And that includes probably the chats and WhatsApp or something. Now, there's 3.5 billion per day, and this is absolutely outdated, this number, I'm sure. So you can do the fact that essentially 7% of electricity now is produced by Googling. Which is a problem, essentially. So we need to do better. Particularly you need to do better. Our generation probably won't suffer it, but you do. So that is one grand challenge that we want. And then the connectivity. The connectivity, it comes a little bit funny, and I'm not sure if some of you may be aware of it, of this idea of terahertz communication gap. We can communicate very fast with fiber optics, optically, very quickly. But in the regime of terahertz, between 0.3 and 3 terahertz, there is a bit of a bridge, where the electronics can go up to that level. And then there's a bit of a bridge that is unstable in between to actually communicate with the optical part. So this is another part that essentially is creating that connectivity problem to actually, it comes together with efficiency. So the idea is to try to actually engineer efficient, you need to create materials that compute efficiently, that connect better, and that do it quickly. So all these three models together in terms of looking at this physics. And Spintronics, of course, brings it up in a very nice way. One of the aspects that you will hear from Thomas Youngworth, a longtime colleague of mine that we've been working for a long time, is to think perhaps about antiferromagnetic materials, which before maybe 5-6 years ago, 8 years ago, they were thought primarily as passive materials, because these are materials that have not all the spins aligned, you have net zero magnetic moment. So itself, it has the advantage that it is insensitive by definition to magnetic fields. But on the other hand, because of the energy scales on how they actually couple together, in terms of the megahertz that are typical, or gigahertz that are typical, gigahertz that are typical of a magnetic resonance in ferromagnets due to the anisotropy energies, here you have terahertz energy to what is called the exchange enhancement effect. So they tend to be 1,000 times faster naturally because of the ordering that they have. But once again, it's difficult to manipulate them. Essentially, Neil mentioned that they tend to be very interesting materials, but useless from a point of view of application, perhaps. But unfortunately, he was wrong. There is a way to exploit this idea, this notion of creating these antiferromagnetic CADs. And this by borrowing from this notion of using this Edelstein inverse spin galvanic effect in a ferromagnet that has, in this case, two sublattices that have each of them opposite broken inversion symmetry. If you do have that, this particular material, in this case, happens to be copper manganese arsenide and manganese to gold. That's another one that we predicted in 2014. If you run a current through them in a particular direction, you would be eventually able to flip it. It would be similar as if you actually are coiling with different directions, the different sublattices. So the chirality of the coiling in each of them here, you can see is slightly different. And by running one current through one direction, you will be able to flip it. And I want to remind you that in antiferromagnet, it really is 90 degrees that actually you make a difference between the directions, not opposite, because here this and that is the same. Up and down is essentially no difference from the point of view of detection. So by 90 degrees, you can flip the systems. It's kind of creating this current-induced anisotropy that you're able to twist your antiferromagnet and then read from normal anisotropic magnetoresistance, which tells you about the relative orientation of a current and the orientation of in this case, the Néel order parameter, the antiferromagnetic order parameter, the actual direction. This is something that the nice thing that it was predicted, and then less than a few months later, it was predicted manganese to gold, but in copper manganese arsenide that has the same band structure, they happened to have it in the Nottingham lab, and they were able to run the experiment, and for the first time observed by an electric current, not by huge magnetic fields, that is usually how you actually manipulate antiferromagnets. You were able to actually switch the antiferromagnetic order of the antiferromagnet. So you bring all of a sudden this huge number of materials that are around, which actually there's a lot more antiferromagnets than ferromagnets. Ferromagnets, we actually are using very few of them. Very few are practical enough, but the plethora of the antiferromagnetic order is much more stable or abundant in nature. If you actually look at the different elements that have this type of ordering. So now all of a sudden you'll be able to switch this guy, okay? And not only that, because this happens to be essentially a resistance measurement that you actually measure the different directions. They were able to check that the moments were flipped by doing X-ray magnetolinear dichroism. So you have to double check that it's not only the resistance, but also the moments are actually flipping. But once you are convinced that that is the case, you can simply use that as a fact and put it in a chip and detect it. So this is, for example, and this is why I wanted to emphasize of the Spintronics rapidity of some of the discoveries. The notion that you could do this to an antiferromagnet was unknown in 2014, essentially 6-7 years ago. Not even the Russians had thought about it, which is actually amazing. That's actually one of the things that you should be very proud of, is try to do something that a Russian didn't think about before. If you do manage to do that once, you're into a good thing, yeah? Because most of the times by symmetry, they won't discover it. But in this case, they didn't. That's nice enough. And going from the prediction to the discovery of the effect to the actual putting on a device, because this that you see is the first MRAM, antiferromagnetic MRAM technology in your life that you've seen. Not sure if it will be practical. Maybe your kids will use it in their new computers or something. But in this particular case, it has an advantage because this one, it is done electrically, but you could also excite it almost optically. So now so you go from prediction to discovery to device in less than a year, which is even for any standards, fairly rapid. But then you actually can also use light to excite it, because here, this is actually something that the antiferromagnets, being in the terahertz regime, they can actually, this is an experiment, you can do the experiment now both electrically, but you can also do the experiment optically, which is in that communication gap that I mentioned. You always try to address these grand challenges ahead of you. And there you cannot see the difference between them because the mechanisms are effectively the same. The mechanisms are driven by electric field. And as long as are within that time scales of the excitation of the system, which are terahertz, you are able to still switch it. This brings the whole thing to the terahertz, to the optical regime, which is fairly exciting in terms of speeds. You've now been able to not only do it more efficiently, but doing it much, much faster. So now you have this communication gap naturally bridged, because these materials are naturally in that communication gap of the terahertz, the antiferromagnets that tend to be. So that, one of your models, that it is kind of naturally given to you by that process. But what about the higher efficiency? And this is where we go into something that Julia will tell you about. And again, there's many other, unfortunately, given the time, I don't have the time to really cover every single topic that has been discussed. So here's just a story that connects several of them. And this higher efficiency comes into the notion, going back to how much water you're boiling every day by your Googling. Now, if you do that, then you come back to the notion that perhaps we should look at how efficient we ourselves are. The brain, what your brain actually does, using only 20 watts, is done usually effectively by a supercomputer, digital AI computer, where it tries to do the similar things in that same format, but using 1,000,000 watts. So the ratio of efficiency is huge. If we can actually create this massive parallelization that is actually in the neuron, where essentially both the signaling and the processing and the memory are embedded and integrated together, is a huge step. Now, they've managed to do now AI quite a lot. So the artificial intelligence has had huge effects on your life and on our lives, and particularly nowadays, somebody that lives in Germany like me, when I moved here, I knew not German, and it still is difficult. I have a lot of, my German is very archaic, I cannot teach in German at all. But as you may have noticed, 6 years ago, you translated in Google, and then it was a very funny translation. If you do it several times, it was unrecognizable. And in a short time span, it has created translation using AI.com or something like that, where it's extremely efficient and very good, where it actually creates these communications very efficiently. These are where you have this difference between a classical computer and the brain. In a classical computer, you're very slow. It's kilohertz, essentially. Sorry, in a classical computer, it's gigahertz. In the brain, we're actually fairly slow, kilohertz. This is why, runners, essentially, if you actually react within a 1,000th of a second, it is a false start. Even if you are simultaneously running on a sprint run, because your brain cannot physically react that fast. In our case, we're analog. The other one is digital. The other one is rigid hierarchy. The other one is disordered. The other one is synchronous driven. Ours is asynchronous. The computers tend to be sequential. If you do it once, they will all be the same. In this case, we have this massive parallelization that we use. There's a logic separation and memory separation using Neumann architecture. And this is where we go to the non-Neumann architectures that we actually proposing within AI. There's a minimum redundancy in your computers, whereas in our brains, there's huge redundancy. There has to be. When I forget one thing, I'll remember from another. And as you get more gray like I do, you forget even more. Now, so it's good that the computers have well-defined problems and iterative tasks, and the brain tends to be good at ill-posed problems, cognitive tasks, etc. And here you have different hierarchies of what you can do. Here you have different architectures from the very lowest to the maybe higher of Simpson to the top one in terms of the brain architecture that you have. You can guess of how I go politically. And then, but the nice thing with machine learning and deep neural networks, which is essentially what the brains are created from, this is pattern recognition, and deep neural networks are using the exact same trick to do picture recognition, audio transcribing, text translation, geometry, etc. Using all of it similar tricks where you have these essentially different layers that you're created, but you need devices that actually have this memory effect to them, where you have some trigger that you have a memory and then it decays and it doesn't remember for a little while. And then with this type of networks, you could create such artificial brains in effect. You can create them in the computer by essentially mimic what a neuron and a synapse does. And this is, but the efficiency is lost in this case. You should be, maybe just to give you an idea of where AI is now, if you can see these people, they look like famous people to you, right? So these are non-existent people. These pictures are generated by a number. And the computer, after having learned how people in the red carpet and all these guys look like, is generated by itself without any guidance. These people, you can see that many of them look pretty good. This one didn't look very good. It looked like he had too much chemistry in his hands. Sometimes it doesn't work very well, as you can see, but sometimes it's going to be hard to distinguish. These deep fakes are real, unfortunately, and these are literally, they came generated by a number, by this network that it was actually self-taught in a sense, similar to how we are self-taught by this in our brain structure. Highly efficient, but very slow. So this is, of course, where you connect a little bit to the antiferromagnetic spintronics. It turns out that these devices, the antiferromagnets and the systems that you have, if you actually look in here, and I didn't want to really amplify on this, so maybe you will go into that, you do have this behavior that you need from the device to be effectively a synapse and a neuron at the same time. Now, in here, in this antiferromagnetic, you can actually see you have bridged the communication gap. So now you have access to most of the information in the world very rapidly. You can connect to the Internet of Things because you have also electric connections to them. And you have a means to do a natural synapses and connections. But there's a difference between our brains and the brains that you would create artificially, because you want to go back to this analog, similar to what Julie Goulier is doing, and some of the folks are doing, where you're not doing it digitally by having a digital computer mimic what, by different instructions, not so efficiently, what the other ones actually, what the neuron is doing, but the physical device doing it itself. Now in here, this is a little bit of a trick, because here, this is terahertz speed, not kilohertz speeds. So this is 1,000 times, 1,000 millions, a billion times, approximately faster. This is what it means. If you actually create such a thing, eventually, you seriously should think about turning it on or not, because it will decide very quickly whether to keep you or not. Within essentially the self-learning algorithms that you create, you could have essentially, you learn the entire history of humanity and all the probably different aspects within a few minutes, and project what you would be predicted and see how good we were for humanity or the world itself or not. The computer may decide that we're not so relevant after all. It's a little bit of a leap, of course, but this is where you also have to come in as a scientist, where your science can also have huge repercussions on society. Spintronics has had huge repercussions on society. We've created the World Wide Web. We've created essentially this notion of cloud computing, which allowed social media, which allow us today to actually communicate how we are communicating. This is the science that we created. We started from the lab, of course, motivated, just like Feynman, for very totally different unpractical reasons of why we do it. But it has huge consequences, and also on society, which we're responsible in part for. So once you get into this realm of things, make sure you actually think about it. So this is a little bit of the story that I wanted to just give you a flavor of how you've seen. This is only a decade of research that actually I've described to you. And some of it actually within 6 years of research, essentially not much longer than you will do your PhD. And this has come from where you can create these magnetic cuts to make them available in artificial intelligence, creating this circular revolution that you started from analog, you went all this fully to digital, and you may go back to analog in this circular notion that you have. Now that means that, of course, and then this is my last slide, so I don't want to go too much over time, and I think it's more important that we talk to the students and they ask the questions, that in this school, the opportunity of Spintronics, why Spintronics, is because this is what you will learn in this school. Yeah, this is all the huge physics that have created impact in society that you will learn here. And this is the one that is left for you to discover. So learn well and make sure you lift up a lot more from this iceberg. With that, I would like to, of course, thank everybody and the organizers to have me, but also the team that creates a lot of the science that I described to you, and particularly Thomas Youngworth, that you will hear from later in the school. As a collaborator with me, I've been actually part of the Institute of Prague, Physics in Prague for now, as long as I've been married as well, like 30 years almost together. But also from a fantastic research scientist that had a lot of these concepts, Libor Schmeichel and Helen Gomonai, that are within our teams, both within Prague and Czech Republic, and the many collaborators that we've had. So with this, I think that's all I wanted to maybe cover in this rapid overview of where you can go with Spintronics, why it's so exciting, why these discoveries happen to be so connected and go from one to the other, and take any questions you may wish. So, everybody okay? That's the problem. I think we don't
Thank you very much. Thank you very much, Jairo. That was excellent. Very good. I enjoyed it a lot. I'm sure that the rest of the audience is thinking about questions. Yeah,
it's a bit overwhelming, of course, but it's just to give you an idea of where we can go. So you can also ask philosophical questions, because the real tutorials are coming in a minute.
Yeah, I understand this is a great introduction. And in this introduction, you have given us a very nice overview about why we should be interested in Spintronics, and that is not only the applications, but also the applications, but not only. And before we start with the questions, and while people get to manage with putting the questions in the chat, please remember that you can all use the chat for questions. You can also use the microphone for questions. While they write the questions in the chat, I would like to put a question of myself, and that is, when you have to tell to a more general audience, not only students who already know something about Spintronics, but it is so important that we communicate those things to society. So if you want to tell people who are not familiar with magnetism what Spintronics is, what it is, how would you do it, Jairo?
And you always have to go with what people, it's about the audience, not about us. Yeah. What is important to you? Your friends, how you communicate with them, the iPad that you use, the technology that you are relying upon, the idea that you've came from, this lab to the hand, this technology that has shaped society, unfortunately, in good ways and in bad ways, and told them about these things. Well, if this is important to you, would it be better to communicate more efficiently? What about the effect that your communication is having on the environment? How do you deal with that? And then by bringing these problems that are important to the people, and saying that these are the problems, these are the grand challenges that we're addressing. Some of it, unfortunately, we created with this technology that we gave you. And the idea that now, even in COVID times, you still could communicate with your friends, with your family. This is technology that, of course, not only us created it, but this first step had to be at the basic science level. If you don't have that first step, you will not generate it. So if you don't invest on that first step, you will never discover these new things. And there was no notion when I first predicted this intrinsic spin Hall effect. There was no way in hell, I can assure you, that was 20 years ago. I can promise you, I thought it was a cute idea, but I never, ever imagined that it would be in the spin orbit torque ESpinRed technology. And it is now used. It's incredible how rapid this thing has changed. You don't know where the next opportunity will be, but you do know that it is. Without it, you will not open the opportunities. And a lot of these things come about integrating between different areas. We now becoming very specialized before. And now in society, it's really, really important to actually address your science in a way that it also connects to things that are important to everybody. Not just simply, don't ever go to somebody, I always tell people, like, if you cannot explain to your mother what you do, assuming she's not a physicist, yeah, you don't really know what you're doing. And it has to be that. You have to communicate a little better that way. And it's just about simply what is important to them. Yeah, I think try to do. I mean, part of this talk is I adapted a little bit of this talk to a public talk that I gave in the KITP in Santa Barbara, where of course, this idea of society and the fact that the computers will kill you appeals to a lot of people. Yeah, but in this case, it is not too far off in terms of the mess that it could create if you do actually compute it, because for the first time, you see the possibility that it could happen. Yeah, at least to create that artificial brain, which is scary. Is there any questions maybe from the?
Very good. Yeah, there are questions are coming. And here we have a first question by Ron Golford. Ron, we're very happy to have you here. And the question is, self-flipping ferromagnets with internal transfer of angular momentum, like in falling cat, is very appealing. It would seem to require no energy input.
No, it does require, unfortunately, energy.
Yeah.
It does, because all of these things has. Sorry, it was. I should finish.
Yeah, the question came actually: is the process stochastic, thermally driven? Or do we have to drop a ferromagnetic memory device to see if it switches and lands on its pores?
Yeah. So in this case, unfortunately, we don't create an ubiquitous permanent moving machine, of course. In here, you do require an electric field, a charge, a current, actually creating such an internal flipping of the device. But in this case, these tend to be metallic systems, which tend to be fairly efficient. So in that sense, what you're doing is essentially trying to create a faster way of switching and connecting memories with the processing by creating an electrical magnetic memory. This is really where the fission is coming from. It's definitely energetically driven because you do have heating, you have a current. Unfortunately, you don't get away from it, from being free. But the fission comes from the integration of the structure, similar to how we have, of course, are using electricity in our own brains, but in a highly parallel and efficient way. And this has been, of course, for the ESpinRed technology, for the spin orbit torques, ESpinRed technologies. It has also consequences on speed on itself. So that's also been an advantage.
Yeah. Great. Yeah, it seems self-flipping has attracted quite a lot of attention. We have another question about this. It's Jose Solano asking, thanks for the nice talk, Jairo. Could you expand a little bit about how the effects leading to the self-flipping and what materials are or expected to be good candidates for this self-flipping?
Unfortunately, yeah. So this flip, these magnetic cats, unfortunately, these are usually systems that are ferromagnets, and also in this case, antiferromagnets, that have broken inversion symmetry. And unfortunately, there's not many of those candidates. You know, iron and things like that, they're centrosymmetric, and they don't tend to have that effect. For antiferromagnets, also the materials themselves, the candidates are not so many there. But this notion, the basic idea is that you have an internal spin-orbit coupling. When you run a current through this internal spin-orbit coupling, that creates this moment, a magnetic field in momentum space that point in a particular direction, depending on your current direction. And that also tells the magnet to say, oh, you know, the magnet wants to align with an effective magnetic field that you create. So essentially, if you're able to create that one in a particular, that depends on the direction, you're able to then switch it in that direction. But to engineer that, essentially, you have gallium manganese arsenide was our, you know, an easy candidate to do, but new candidates are difficult. These flipping magnets, unfortunately, in technology do not exist yet. Antiferromagnets, on the other hand, could have more of a notion, and there's been a lot of drive to do that. But there's a lot of new physics that we're understanding that is not only what the concept that we discussed, but some of it has to do with heating, etc. But the possibilities are there. But you want to drive where you electrically switch or control the order state. And if you do that, you create a lot of efficiency. So you couple the electric manipulation of spin. Tends to be something that is very appealing for technological purposes.
Great, great. Still another question about materials. Dylan Perez, who says, hi, thanks very much for your talk. Could you tell a bit about how Spintronics can mesh with new exotic materials like 2D materials like graphene, and what impact?
I mean, they already are. You do know, of course, actually, one of the speakers and our organizers, Stefan, will be giving you a beautiful overview of the magnetic 2D materials, not only graphene. He's also a leader actually in the graphene business, but graphene is actually in graphene. You have these spintromic notions by bombardment and creating these vacancies that are magnetic, and to actually create a spin Hall effect effectively and some magnetic effects in graphene. Not as efficiency, unfortunately, is turned out as in other materials, but now these 2D materials with the concatenable lattices that essentially create this strong spin-orbit coupling in 2 dimensions have a huge advantages. Some of them is because of the control of the dimensionality and the efficiency that comes along with it by going from 2D to from 3D to 2D, and the fact that you have a magnetic order in these systems that before it was not thought to be possible due to the Marmin-Wegner theorem, but now due to other reasons is that they are definitely stable. But this is not the only material. There's lots of new materials. Now the antiferromagnets also are this antiferromagnetic 2-dimensional materials, but also the 3D we've discovered, and that is something that we just put out a week ago, a totally new class of antiferromagnet that is actually not an antiferromagnet, not a magnet. We call it altermagnet, which can actually be used to create one of the most efficient GMR devices in the world, because so this is about looking at symmetries, looking at the different materials, the opportunities that you will see, and they have a beautiful 4 lectures there that you will see all of these, many of these possibilities are not the only ones, is the world of materials. And this is where artificial intelligence and search of materials based on artificial intelligence searches are going to be quite important. So it's also a new revolution for theoretical physicists. That before they thought they would never use artificial intelligence to do it, but we have to. It's coming. You don't have a choice.
Excellent. Manu Astani asks, are the spin transfer MRAM commercialized?
At the moment they are. Of course, these are based on the STT, so the STT MRAMs. The spin orbit torque MRAMs, I don't know, it's Toshiba that is doing it essentially, but it's all in Korea Peninsula, that's the one that are developing, but they're not as widespread as they are. They essentially, they are niche in the market at the moment. but the moment that you can buy them. So essentially, yeah, the answer is yes.
Right. Then Raul Gupta says, thank you for the nice talk. In your opinion, would you think the antiferromagnetic spintronics can be used to make qubits? Any comments?
That's a good question. At the end of the day, qubits, you want to be fairly insulated. So antiferromagnets can be a good notion because they are insensitive to magnetic fields. But in the world of spintronics, most of the time we drive ourselves to connect to it, to manipulate it. So we're a bit of anti-quantum computers ourselves, because anything that you start introduce spin-orbit coupling or things to manipulate, that is a knob that will deface your qubit often. So you should never say no, because actually I've actually created, made wrong predictions before on that. It would be exciting to observe some of them. But yeah, that I don't quite know the answer to that. Here, most of the qubits are now, of course, they're creating superconducting islands. There's a lot of physics, by the way, connected superconductivity and antiferromagnets. That could be a very nice notion of that. But to see them as qubits themselves, difficult to see. No. And I'm not an expert on quantum computing, so let's just take it with a grain of salt what I say. Should always take with a grain of salt what I say anyway.
Pradeep asks, could you please, actually there are several questions in one. Could you please explain a bit more about how the magnetic cut is transferring the angular momentum in itself to get switched? That's the first question.
Yeah, so what it is essentially, spin-orbit coupling can generate this angular momentum. And you're wondering yourself, where does angular momentum maybe go? When you drive this current, you're magnetizing, or proportional to the current, your conducting electrons. So these conducting electrons create this magnetization that is not in the direction of the magnetization of the local moments that are the ferromagnets, the other ferromagnets. Now they couple to each other, they like a normal effective magnetic field, and then they want to align effectively. Now this angular momentum is generated cohesively, but at the same time, where does it go? Where does it relax? Because if you flip at some point, you need to relax. And this is where the effect of the lattice comes in. You should think of the lattice of a material as a gobbler of angular momentum effectively at the end, where essentially due to the spin-orbit coupling also, you will eventually have a drain of that angular momentum, you will relax to it. So you generate it coherently through this current, you flip your ferromagnet, and then that should relax. If it's stable in that direction, of course, you would be staying there. So it's a bit like, how would I say it? I don't have a good analogy. If you have kind of like, if you have a bucket of water, yeah, and then you're rotating, essentially stays put. But if you stop, eventually it flows down, yeah, the water. Maybe that's a little bit how you generate it. But
yeah, clear.
I could, better not to show. I can show you the equations, but equations don't help. I don't think in this case. This is not today. My lecture is not for equations.
Yeah, not at this time. I think this was great. The other question by the same person is also, you mentioned about distinguishing the torque from a Spen-Hall effect and Edelstein effect by ferromagnetic resonance. Could you explain a little bit more about that?
Yes, that one actually you can share. Maybe actually you can slide. Let me see. So I can, hang on a second. That one I can show. Let me share something. Okay. I'm going to share this. Okay. Just you see, maybe am I sharing now?
Yeah.
Okay. So let me share this one. So this is essentially how you actually do the experiment in this gallium manganese arsenide. You drive a current through the gallium manganese arsenide itself, But in an FMR experiment, what you do, you drive a small magnetic field to create that resonance. All right. This external magnetic field in FMR is outside generated by coils, but here you're using the internal momentum-dependent effective magnetic field as the generator. And from the signal that you see, you deduce what this internal magnetic field is proportional to the current. So it's kind of like an inverse FMR technique. And here, when you actually see this resonance as a function of DC, this is essentially, you will have a DC component to this resonance. You will split it into a symmetric and an anti-symmetric component. And the symmetric and anti-symmetric component have different symmetries of the torque that they generate. And effectively, when you do these experiments, the only thing that you can tell is actually what is the symmetry of the torque. What happened before, which was a little bit of a misconception, is that the Edelstein was always thought to be field-like, and the other effect of the spin Hall effect was supposed to be dissipative-like. So in the LLG equation, you have a dissipative and a field-like torque. You can only have the one that relaxes you, and then the one that just makes you rotate, precess. But by doing this magnetic cuts in gallium manganese arsenide, we actually show that that is not the case. They actually are mixed, all of them. And this is where you need to have a material that, depending on the direction, you will have different torques in order to distinguish them. Otherwise, by symmetry, you can only tell in these experiments whether they are damping or anti-damping. You really cannot really tell where they're coming from, because you can argue, many times they call this a spin Hall effect measurement, but the measurement itself is not a spin Hall angle, it's just how much of a damping torque you actually are measuring. So this is also a little bit of, by such a rapid development in our fields, a lot of the language is a little bit lost. So you have to know sometimes very carefully what people are measuring and what people are calling what. Sometimes I call a spin Hall angle of 10, which of course, that makes no sense. If you think about a spin Hall angle, it's like the electron comes and does flip, 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 and then goes away. The spin Hall angle should be quite small usually. But it is just the notion that the torque that you can generate, combination of the spin Hall and the Edelstein effect, is very strong and efficient. So yeah, that's the nature of the things that you will learn, hopefully in the course. Yeah.
Okay, thank you. Thank you, Jairo. Look, we still have 4 or 3 questions, so I'm going to ask you if you can maybe fast answer some of them, because we need to very soon go to next lesson. But I'd like people to get their answers. So maybe I can start by Eric's question, that is, can the ferromagnetic or antiferromagnetic 2D materials work in room temperature?
I believe some of them do have TCs close to room temperature. So essentially, it is all about finding strong anisotropies enough, and some of them can be engineered. I think you will need to ask the experts later on to see which is the range. But I think there will be a Nature review with Stefan and Kobayashi that have led that work, that they put some new materials, and it's all about the transition temperatures, the nail temperatures to be high. In the antiferromagnet, they can be high often. Great. Many of them don't, unfortunately.
Yeah. Okay, then Jose Angel Fernandez Roldan. Hi, Jose Angel. He asks, nice talk. I guess most of the Spintronics is in 2D materials. What are the current challenges of 3D Spintronics and 3D antiferromagnetic Spintronics?
I'm not sure why he's saying that, because I would say the majority is actually on 3D materials still. Thin films are still 3D materials. They do behave like, you maybe think that because you have thin films and the magnetic structure looks like 2D and you're observing that, or it's a flat system, but it's still 3-dimensional. It's strictly 2-dimensional, which is the materials that are coming are just emerging. They're a bit of a fringe within it. You actually have more. I think you may refer into the fact that the disk and the skyrmions themselves, you look at an effective 2D structure, but the materials that we study and the things that we generate, the majority is still 3-dimensional. And here you have components on anisotropy that you can do. Also in the skyrmion physics, you actually are now going to the Shankar skyrmions and the three-dimensional skyrmions. Whether they can be practical or not, who knows? They're beautiful physics. That's what it matters. They're gorgeous physics. And gorgeous physics tend to actually be useful, like a gorgeous wine. Yeah.
Well, I think actually Jose Angel wanted you to answer which are the challenges of Spintronics right now.
The challenge is to know where to go. There's so many opportunities. I think the biggest challenge is the idea of merging things more. This idea of really finding things that are really more efficient from a practical device technology point of view. The other one is to actually not to be too pleasant and think that everything has been discovered, because it hasn't been. I mean, we were actually shocked a few weeks ago of discovering a total new class of antiferromagnets of order. We didn't know existed. Something that it should have been in every book since the 60s for some reason. Didn't really stay there. So yeah, I think the challenges are many. I think as a student, I think the message would be more for the students right now. Try to not specialize on something too much. This school is a fantastic, gorgeous opportunity for you to really have a broad overview of it all. And what is really exciting is when you can connect between two things. One thing that I like a lot myself and I enjoy a lot, this is why the SPICE Interdisciplinary Center was created. This was actually to bring different areas together. So try to go to workshops that half of the people you know and half of the people you would like to get to know. This is really where a lot of the science, the new science are coming. Discoveries that if I tell you what I'm doing in 5 years, I'm lying through my teeth because many of the things that we're working on now were discovered only a couple of years ago. And that's, I don't think it's a challenge per se, but keep the excitement and really exploring. And what I said about the iceberg of that is left to discover, it is so true. It is so true.
Well, great, Jairo. I think this is a perfect end for your class.
Thank you.
We have all learned a lot, enjoyed a lot according to the questions. And there are many other questions that are asking about challenges and congratulating you for your talk and thanking for your talk.
Yeah, happy to, if you receive emails anytime, if you guys want to also visit Germany anytime. Lots of opportunities. A network, we actually, the Spaniards, by the way, talking to the Spaniards themselves, we're actually now all over Europe. I think Angel Rubio is in Hamburg. I'm here. There's many opportunities to collaborate and visit and explore this network beyond many things. So please do reach out. We're happy to hear from you as well.
Well, thank you very much. I thank you on behalf of everyone.
Thank you.